So last time we discussed the following. So if I've some kind of symplectic quotient, how is this? Is this legible?
Blue's better, right? Yeah. Blue might be better.
Let's try the new black. No, it's terrible. Yeah, blue's better. We can consider some like 3D field theories. Which will be the twists of the n equals 4. And so what were they? Well, remember, we had this kind of cool thing, AKSE thing, that in order to construct a field theory, we needed to have maps from something to this guy where the source manifold is some kind of volume form. So there's 3 of them: the B twist, or Rosansky-Witten theory, where the equations of motion on flat space and in the middle, there was a half twist. And this is not topological. Where this describes maps from C1/1 cross OR to V mod G. And let me remind you, when I have this subscript to RAM, this means locally constant maps. And here, this means in this direction they're holomorphic, this direction they're locally constant. So people are worried about locally constant maps. You think about quantum mechanics, where the topological quantum mechanics, the equations of motion are constant. Doesn't mean it's a stupid theory. So let's rewrite this in a slightly different way. Thanks, David. Maps from like C1/1 to anything, sorry, C0/1 is the shifted tangent bundle of X. The point is, we should think of C0/1 as the spectrum of C epsilon mod epsilon squared, where epsilon is odd. And we all learned from Grothendieck, or whoever, not personally, that if this was an even parameter, this would just be the tangent bundle. But here's the shifted tangent bundle. So we can view this mapping space by using various adjunctions. C cross order RAM to the shifted tangent bundle. G. This is one way to look at it. And finally, well, this super manifold has 2 vector fields. One of them is d by d epsilon, and the other is epsilon d by dz. And these lead to the A twist. And this leads to the B twist. So I want to explain what does the A twist look like. So I want to talk about something I think David explained about today. Turning on this d by d epsilon is very similar to making things equivariant for a circle action. For any x, this is more or less the same as from the spectrum of the cohomology of S1 to x. So it's really these kind of topological loop spaces that David and friends like. But the point is, functions on this shifted tangent bundle are differential forms on x. And this d by d epsilon becomes the de Rham differential. Okay, so finally, what does all this mean for us? Well, this means that d by d epsilon turns this odd tangent bundle into the de Rham stack. Now I'm being sloppy with Z-mod 2 gradings and so on, but there's a number of precise statements along these lines, and one of them is the work of David Nadler and David Benz-V about equivariant loop spaces that David was talking about today. So the final answer is like, what does the A twist look like? It looks like the equations of motion are maps from C cross OR to this symplectic quotient. There's two ways to write it. It's this de Rham stack of this, or I can put the de Rham stack inside. V G. Okay. Why I'm emphasizing this, we'll see why I'm emphasizing this shortly. But the point is, whatever the de Rham stack is, functions on it, or its cohomology, bundles on it, or D-modules, so on, are local systems. So we're going to be considering, for example, operators, or observables in this theory. They'll be built from kind of functions in this space of fields. So there'll be something about the cohomologies of these mapping spaces. So it's kind of related to the cohomology of these mapping spaces. And I think Tudor, was Tudor here? Yes. Will you be talking about vortices?
Yes.
Yes. So this mapping space is kind of essentially the vortex moduli space. And this twist means we're thinking about the cohomology of this, which is what you'll be explaining. So it's going to consistently check that we're talking about the same theory. So what I wanted to talk about today, there was some discussion about, in Tudor's talks, about order and disorder operators. So I wanted to talk a bit briefly about how in these twisted theories one can figure out what the space of local operators looks like. And you can see, we'll see quite explicitly where some local operators we'll find will be built from described by singularities in the fields, and others will be built from just functions on the fundamental fields. Okay. So as recall, so for example, a 3D field theory will assign some M, compact three-manifold, kind of equations of motion on M, which is a shifted symplectic space. Well, what we expect to find in general, suppose I took instead of a compact three-manifold, suppose I took the equations of motion on sigma, across some kind of very small interval. Sigma is a surface. It is compact. So really, we're looking at the germs of the solutions of the equations of motion along sigma. Now, why have this small epsilon? In a topological field theory, the size of epsilon doesn't matter, but in a real quantum field theory, you really want to think of informal series in this variable. What we'll find is that this guy is an ordinary symplectic manifold. The Hilbert space Hilbert space attached to sigma should be obtained by geometric quantization of a symplectic manifold. This symplectic manifold is called the phase space, by the way. Is this too low? Can people see this here, or is it okay? Yeah. Infinite dimensional derived stack. Obviously. No, I mean, it depends. I mean, suppose you were doing some kind of gauge theory, then there'd be quotienting and it'll be a stack. But if you're doing a free scalar field theory, this will be like, the cotangent bundle of a vector space, infinite dimensional vector space. So it depends on the situation. Sometimes it's a real manifold, other times it's all this other stuff. Suppose M is a 3 manifold which has incoming and outgoing boundary. What you find is that the equations of motion on M should maps to the equations of motion incoming across the equations of motion outgoing. And on one of them, you change the symplectic form. This guy is a Lagrangian. This is the heuristic. Of course, you should bear in mind this map may not be an embedding. That's fine. There is, in this fancy derived world, there's a notion of Lagrangian map.
So is this statement pure?
It's probably due to pearls in the 1950s or something in some context.
Okay.
Like every person who ever thought about quantum field theory knows this.
What is for physicists and not for theorists?
Okay, so suppose you give me a Lagrangian, then I can certainly construct this shifted symplectic structure as I was describing. Now, it's not quite proved yet, although I kind of know how it should go. I mean, when we're talking about it, how to construct this. Once I take the germs of solutions, how to construct the only symplectic manifold, there's some kind of transgression. It has to do with the fact that here, the shifted symplectic structure, locally it involved Verdier duality. And if I think of Verdier duality and how it behaves when I restrict to codimension 1 manifold, there's a shift of 1. That's that shift. That's why we get ordinary symplectic. Now, for topological field theories, Nick proved this. Where's Nick? Yes, Nick proved that, P0 factorization algebras. And the algebraic context too, yes. So every example we will talk about is being proved by Nick. Yeah, I've forgotten you did the algebraic one too. That's much harder. Okay, so what do you expect? You expect that Z of M from Z of delta in of M to Z delta out of M. What is this map supposed to be, at least heuristically, is just supposed to be, in geometric quantization, Lagrangian correspondence is quantized to maps. Okay, so obviously it's very hard to construct this kind of thing, especially if everything is very infinite dimensional. This is why quantum field theory is hard. And even if it's topological field theory, you have to worry about all their choices. That's why topological field theory is hard too. But this is like the heuristic of how topological field theory should work. So we want to apply this to our example. So remember Tudor and David were talking about local operators.
Yes?
Cool.
Given quantization is a procedure that's, so to speak, well-defined, once you know, obviously an infinite dimensional space of choices, once you know Z of sigma and this line 1.
Well, it's much, if this is infinite dimensional, depends on more than that because the space of polarizations may not be connected.
Okay. Can a similar statement be made for the quantization of Lagrangian correspondences?
No. So think of a simple example. Think of a function on the cotangent bundle. You can view this as a Lagrangian, some kind of Lagrangian correspondence. To quantize, you want to produce some differential operator, and of course, you know. It's probably better. I mean, maybe if you take a Lagrangian, Lagrangian correspondence inside the cotangent bundle, if it's the graph of a function on x cross x, well, what you'd really want it to be is like kind of the graph of a half density. And then you can quantize it. So there's always some kind of ambiguity, like just the ambiguity that always appears in any kind of quantization.
In that case, it still feels like choosing a polarization, though. Sorry, I can't see it.
Pardon?
In the case of quantizing like a function to a differential operator, it still sort of feels like choosing a polarization, right?
Yeah, but well, no. You just have a symplectic vector space with a function on it. I mean, you can lift to an element of the Veil algebra in more than one way.
Absolutely, but
So
somehow there's a sort of that's like choosing a normal ordering feels a lot like choosing a polarization of a symplectic manifold.
Yeah, but I think it's more than that because even if you have a polarization, I mean, there can be like cases when this guy just does not lift. I mean, some algebra in the classical guy does not satisfy the commutation relations in the quantum one. No matter what polarization you choose. Okay, so let's apply this to our example. So kind of consider local operators. I think this conference is really the 3D n equals 4 theory conference, which is in the 3D n equals 4 theory. Well, local operators should be the Hilbert space of S2, which is supposed to be geometric quantization of equations of motion of S2. Let's calculate this in two examples. So the first example is the B-twist, Rosansky-Witten theory. Then equations of motion on S2. This is maps, locally constant maps from S2. The symplectic quotient. Now, in this kind of stacky world, you often don't lose very much if we replace these kind of locally constant maps, if we replace this guy by the spectrum of its cohomology. In this case, it turns out we lose nothing because it's simply connected. Now, the spectrum of the cohomology of S2 is C mod epsilon, C join epsilon modulo epsilon squared, where epsilon is even. So this, up to grading issues, is just the tangent bundle. And because this is symplectic, it's the same as the cotangent bundle. So now we understand the Hilbert space. So Z, in this case of S2, just functions. Okay, which is the answer we would expect for Rosansky-Witten theory. And as David explained, that this is an E3 algebra, is E3, well, which is more or less the same as commutative plus some kind of even Poisson. And in this picture, this is a Poisson algebra in the obvious way. And obviously. And this is the E structure, the E3 structure. Okay. So I think this is, David will talk more about tomorrow. This is like the Higgs branch. The Higgs branch is some Poisson manifold and Poisson structure coming from the E3 algebra. And so now let's try the other side, A twist. So I want to introduce some notation. Suppose I take any u inside of C cross or open. we set Bun-G of U. These are bundles with a partial connection which looks like kind of A dz bar, AT, ET. In other words, with a holomorphic structure in the C direction, a flat structure in the O direction, and these are compatible. Does this make sense? I mean, you know, we have a codimension 1 foliation, codimensional 1 complex foliation given by dz bar plus dt, and I want a flat connection along that foliation. So I have this connection and kind of the partial curvature of this guy in the dz bar dt part. Okay. So we want to take equations of motion of the two-sphere. Now, inside of C cross OR, our theory is really, our theory looks inhomogeneous because our equations of motion talk about bundles which are holomorphic here and constant on OR. Maybe it really is homogeneous, but if it will be homogeneous in some extremely subtle way. Oh, and also I forgot to say, let's consider, for now, the v equals 0 case. It's the case of pure gauge theory. So instead of using S2, let's use the cylinder. Equals the disk cross interval minus 1, 1, where I remove the origin. Okay? So we wanted to consider the equations of motion of our theory on this. We find that the equations of motion in this A twist, and again in the pure gauge theory case of this cylinder, is the cotangent bundle of Bun-G of this cylinder to RAM.
Just so I can keep up.
Yes, too fast. Yeah.
The fluid's equations of motion, they always need maps to some stack.
Yes.
And the stack in question here
Is it's the cotangent bundle of the RAM stack of G.
okay. And the thing you're mapping to it is C cross O, but viewed holomorphically along C and sort of locally constantly along O.
Yes.
Okay. And what does the words pure gauge theory mean?
Well, we started with some representation of the group and some group.
Yeah.
That representation is 0
Okay.
for simplicity.
What is cotangent bundle of the Durand stack?
Oh, well, it doesn't really do anything. Yes, it's true.
Zero cotangent space.
Yeah, absolutely right. This cotangent bundle doesn't do anything because the RAM stack is 0 cotangent space. It's useful to keep it around.
So
The reason it's useful to keep it around is because in the half twist, the RAM stack degenerates to the double stack, which does have an interesting cotangent bundle. And if we want to think about geometric quantization, we have to figure out what polarizations do we use. And
right, but just as a stack, it's the same.
as a stack, it's the same thing. Yes. Okay. So therefore, we should expect that the Hilbert space, let's call it the space of local operators, are functions on this guy RAM In other words, like the cohomology.
Sorry, what do you mean see if you're the best?
Well, I mean, we're kind of pretending it doesn't really depend on the shape. I mean, it really won't depend on the shape, but there will be subtle kind of issues, which makes it more convenient to use this shape. And they should be kind of local operators. Okay. And so the next step will be figure out what this funny gadget is. And we'll find it's something every geometric representation theory will love. And then a theorem of Bezer-Kabanikov will compute this algebra. Oh, you know, I feel really embarrassed. I forgot to mention. Well, I forgot to mention the origin of this story. So as Tudor is explaining, so Tudor, together with Davide Gaiotto and Matteo Bullimore, have been computing this algebra of monopole operators. So subsequent to that work, Davide and I started thinking about a different approach. So what I'm explaining now is a different approach, which came after Tudor's approach, to computing this algebra of monopole operators. And so it's joint work with Davide.
In terms of not making Nakajima's approach.
I know, he kind of scooped us. We were like working on this for like since months and. So then we thought about how to generalize it a bit. So here we go. I haven't seen Nakajima's approach or anything, but I'm not. That's why I thought he had vortex moduli spaces in it too. But. Okay, so what is this space? Bungee on this funny cylinder. Well, on the bottom, here on the bottom we have a G bundle. P1, P2, a G bundle on the disk. And an isomorphism, P1 restricted to the puncture disk. You know, I have a G bundle on the bottom, a G bundle on the top. Parallel transport in the vertical direction gives me an isomorphism which might have a pole. So if D is the formal disk, then this is something is equal to this quotient. Which is the Affan-Grassmannian G. So we conclude. Okay. So before we get any further, you notice this makes contact with what Tudor was saying about monopoles. Well, we conclude that the local operators are going to be equivariant. It's better to write it as homology. Okay, so what was Tudor saying about local operators? So Tudor explained that to have a local operator, we need to specify some kind of singularity in the gauge fields. What this space is, this is the space of possible singularities we can specify. So in particular, if I have some co-character, the H, then I get this cell. I get a corresponding cell in the Affan-Grassmannian, and with the fundamental task of this cell is to be like a monopole operator. Okay.
So there's a time in Witten's paper with, on geometric line lengths,
Mm-hmm.
which, is this the dimensional reduction of that calculation of line operators?
I forgot, yes, it is. It's related to that, but it's the n equals 2 version of that. So, and I forgot to mention, there's kind of very beautiful work in progress by Phil Sang Yu and Chris Elliott, who are kind of redoing this connection between n equals 4 gauge theory and geometric Langlands using these more holomorphic twists. And they do indeed find that the Affine-Grassmannian and D modules in the Affine-Grassmannian appear as line operators in the n equals 4 theory kind of in precisely this way. So it's very closely related to that.
Can you clarify the difference?
Well, the difference.
Mathematically, what is n equals 4 versus n equals 2G?
Well, we'll see when 4 dimensions. I was going to explain this soon. The line operators in 4 dimensions n equals 2 are coherent sheaves on the Affine-Grassmannian. Whereas, as opposed to equivariant coherent sheaves as opposed to equivariant D modules. Okay.
So maybe this was asked already, but I understand the spec of this thing is supposed to have a description in terms of alignment stool. Can you see that
Yes.
description?
Well, Bezel-Kravenov computed this.
Okay.
And I don't remember his co-authors in this paper. Thank you. Yes. Bezer-Kravenikov. I'm embarrassed. Finkelberg. Gurvich. They computed that this kind of equivariant homology of the Affine-Grassmannian is functions on the symplectic reduction. Okay. So now, this theorem is an example of symplectic duality, because this is like the B model local operators, but for this space, for like a nonlinear sigma model, would target the cotangent bundle of the dual group gauged by the dual group. Maybe as an example. And it's kind of cool. You know, Davide and Tudor and the Bullimore also had kind of more physicsy approach, and they find exactly the same thing. Right? I mean, certainly for SLN. I mean, I've talked to Davide about this, and he seemed convinced.
What I understand, the physicsy approach involves localizing fixed points, and the mathematical proof also involves localizing fixed points. Are they just the same proof?
I haven't got a clue. I haven't looked at either proofs.
You mentioned that in some theory the operators coherent sheaves.
Yes.
G or
On the Affine-Grassmannian. Equivariant coherent sheaves on the Affine-Grassmannian. This is 4-dimensional n equals 2 pure gauge theory in a certain twist. I was going to explain this. Okay, so more generally, great. And of course, I don't want to get in. How am I doing for time, David?
20 minutes, 5 o'clock.
Okay. So more, of course, the product and the E3 structure come from correspondences like, I can think of this as removing 1G. And these are the correspondence Bezer-Kravenov considered too, of course. And you. Sorry. Yes, it goes that way. I've bundles here, Or I can bundle here, I can restrict it to a bundle in each piece. Or I can also restrict it in a bundle where I remove some kind of larger slice. And this space doesn't depend on how big a time slice I remove. So And then I just do push-pull and cohomology or equivalent K-theory or something like that. That's the answer. And more generally, suppose we had matter. What would we find? Matter. Suppose we took this matter to be T star of W, so that we're looking at the target T star W mod G, then we should have the same story, except we use the affine Grassmannian decorated by W, which you can think of as, you know, some bundle here. Let's say. If pairs of G bundles plus sections of the associated bundle on the disk, and an isomorphism preserving the sections. Away from 0. Great, and what do we find is that the vector space is the same. Is just the same. But the convolution product is different. Yeah, so Davide and I are kind of, our project is kind of calculating this algebra, and we expect to get the same answers that Tutor and Davide and Matthew do. And it's very helpful to have an overlap because we already know the answer we want. So. But you can really just kind of compute this kind of geometrically, and you do find the same thing.
You're going to tell us what the answer is?
Well, I can tell you what I think the answer is. Maybe we haven't completely nailed down the non-abelian case. But so here's what I think the answer is. So I'm going to have W invariance in a larger algebra. What's a larger algebra?
W is a Val group? Or
Val group.
W that-
Veil. Sorry about that. The larger algebra is generated by kind of A is generated by as follows. Suppose you write H equals C star to the n. So it's generated by yi plus yi minus xi from I equals 1. And the relation is like yi plus yi minus is equal to product quotient I'll explain what this says it means in a second. Here, rho are roots. Alpha are kind of the weights of the H action on W. On W, kind of x rho, x alpha is a kind of linear combination of xi, these xi's, and so alpha I, rho I, these are the integers which tell us how the ith C star acts. Okay. So for example, in the abelian case, here's an example. Suppose that C star acts on C to the n, and which is this vector space W, then we find the relation y plus y minus is equal to x to the n, which is what Judah wrote. And I think, for example, still a bit confused about various powers and signs, so don't take this super. Don't berate me if I get some kind of factors wrong. And okay. But it's certainly correct in abelian case. Okay, so questions are.
I didn't know you guys up there.
Mm-hmm.
So you said that you explained this distinction that in this three-dimensional n equals 4 case, these things were D modules and G mod G mod G.
Right.
When did you learn that it was supposed to be D modules?
When we with the drum stack, yes. So when we did the holomorphic twist, we had this thing which looked like C1/1 cross R. And we had two symmetries, like dd epsilon d by dz. So what we learned, if I take this kind of mapping space, C0, 1 to x, this is the odd tangent bundle of x, and then the symmetry d by d epsilon becomes the de Rham differential. I mean, the odd tangent space of x I can view as the classifying space of the tangent bundle. So the Higgs stack, the thing whose bundles on it are Higgs bundles. So turning on this d by d epsilon is a deformation from the thing whose bundles are Higgs bundles to the thing whose bundles are D modules. So now this always, very many supersymmetric field theories can be written down in this kind of language with some kind of super complex manifold, and always these d by d epsilon things turn on some de Rham stack. Okay.
Maybe even more explicit, perhaps. Okay. What are the next, three sentences you say to convince yourself that that thing you told us about the one that is being given by this algebra, equivariant D modules of this thing.
Mm-hmm.
And I should ask you to repeat what you said before.
Well, I mean, that was what that was kind of why I didn't just tell you the answer. I wanted to start at the beginning. So I mean, the argument was, okay, we have this thing, we turn on the de Rham stack, then we see that the equations of motion is the de Rham stack of some moduli space. So the Hilbert space is built from geometric quantization. We're doing geometric quantization on some kind of de Rham stack. We're going to get functions on the de Rham stack. And that's the argument, which is cohomology. So, okay, let's move to 4 dimensions. Kind of the n equals 2 in 4 dimensions has a holomorphic twist, which can be described by maps from C2/1 to this quotient. Here again, G is the gauge group of our theory, V is a matter representation. Then there's some kind of residual supersymmetry, which is given by the vector fields d by d epsilon, epsilon d by dz1, epsilon d by dz2. So there's 3 possible twists, but I can take this guy or some linear combination of these guys, but really I can just anything I build from these guys can just be rotated into one of the variables. So there's really only 2 twists. 2 twists left. The one is the d by d epsilon. Well, as we just discussed, this kind of thing always gives you some kind of de Rham stack. So the things when you get a de Rham stack, they're about counting solutions of the equations of motion. And here, what are the equations of motion? Holomorphic maps from this guy to this stack. So it's like a G bundle, holomorphic G bundle on C2 with some sections of V. So this, counting such solutions, this will give you the Donaldson twist. Okay, this I find hard to understand, but this is the kind of thing most people like to do. The other twist, say epsilon d by dz1, this is totally topological. Gives you, what have we done? We've turned epsilon into dz1 and turned on a de Rham differential. This gives maps from C2 cross R2, sorry, C d bar R2 de Rham mod G. So they're again holomorphic here and constant here. So this twist was introduced by Kapustin. So this twist is mixed, holomorphic and topological, and it was introduced by Kapustin. Okay, what am I doing? What's the time?
10 minutes.
2 minutes. Do I believe you?
Where did I sit last time?
Oh, there are other vector fields. I wrote down these 3 ones because these are the ones which come from the supersymmetry algebra of the original guy. Oh, well, just because if I took d by dz2, I could just change coordinates into d by dz1. So there's really only 2 of them. Yeah. I mean, for some nice cases, there's superconformal symmetry, which can be also written down in some other vector fields. Okay, so what is... So I think the last thing I want to explain is why we find coherent sheaves on the Affin-Grassmannian. It's a category of line operators. Let's kind of understand line operators. In the Kapustin twist. And let's do the pure gauge pure gauge. So, as I hope, David, have you explained this already? How line operators are the Hilbert space for a two-sphere in this case? Okay. Well, we'll bear in mind that. So David will explain that, in this case, line operators in a TFT, say of dimension 4 in this case, are this category. Now, this is not a topological field theory, but if we're looking at line operators in the topological directions, it's sufficiently topological that this argument applies. So again, kind of as before, we take our two-sphere to be this kind of cylinder. This is topological, it's holomorphic, and we find that Z, the equations of motion on this thing. Again, let's do, for simplicity, again, the pure gauge case, which is simply the cotangent shifted by where's Phil? Should the shift be -1 or +1?
1.
+1, you think? Okay. So as you can see, the argument I'm doing here is really parroting an argument developed by Chris Elliott and Phil Sang-Yu, where they've mostly focused on the n equals 4 theory, but it generalizes very easily in n equals 2 case. Again, we assume that v equals 0. So it's equal to kind of the shifted cotangent bundle of this double quotient. Now, how were we supposed to figure out what this category is? Well, we figured out what the Hilbert space was by geometric quantization. Here, we're going to do a higher geometric quantization. quantization, we kind of declare by the statement that geometric quantization is the right thing to do, that line operators are coherent sheaves. This is the pure gauge case.
Is this the definition of geometric quantization of line operators or coherent sheaves? What do you define this?
Well, anytime you have a topological field theory, the Hilbert space of a codimension 2 guy, codimension 0 we find a shift by -1. Codimension 1 we find a ordinary symplectic. Codimension 2 we find a shift by +1. And we expect to find a category. So if we have like a shifted symplectic manifold, a shift by +1, we should do geometric quantization to produce a category, and we should do this by choosing a polarization. Maybe you'll get a gerb on the basis of the polarization, replacing the line bundle, and then we take sections of that gerb. So if we believe geometric quantization is right, then the category we assign to this two-sphere is this category, and line operators are by definition the category assigned to this two-sphere. Okay. Now I'm pretty sure this is the right definition of what line operators in this n equals 2 theory should be. Well, I'm not sure I've convinced all the physicists this is the right definition, but you know, it's maybe one more point, then I'll stop. I mean, you can see it's a mixture of like a 't operators, because I could take some cycle in the Afton-Grassmannian, where I declare my fields of some singularity. That's an a 't operator. On the other hand, I could take a vector bundle supported at the origin. That will be acted on by the group. That's a Wilson operator. So this contains both the 't and Wilson operators and mixtures of them, which is what you would expect for n equals 2 theories. Okay, so I'll stop there.